the goal of this lecture will be to find a criterion for when an ith power and a j power are the same, where the base is an element of a group G and the exponents are I and j are both integers. Now the criteria is how these I and j are going to be related. Now the criteria is not as simple as saying that the I exponent is equal to the j exponent. That's not always the case when you have an element A in a group. So all we're going to do here for this particular lecture is to point to the criterion on how to know when these two things are equal depending on the exponents I and j. So before we start everything, so I'm gonna give you a little bit of a review on three things. The first thing is what the order of an element A in a group is. The second thing is the division algorithm, and we need this because we're gonna use this in one of the proofs. And the third thing is the well-ordered principle, and that's also going to be used in one of the proofs. All right, so let's look at what the order of an element of in a group is. So let me read this for you. So the order of an element A in a group G is the smallest, and that's the most important part of this, is the smallest natural number, so that element A to the n power is going to be equal to E, which is the identity in the group. Now, important again is the smallest. So it is possible that you have an A to some power and is the identity, and that exponent there is not the order. The order is the smallest with that property. So let me emphasize that again. So what that means is A to the n will be the identity, and anything that is below n will not give you the identity. What I mean by that is A to the n minus 1 power is not the identity, A to the n minus 2 power is not the identity, and so on. So the notation we are using for this is bars of A, and bars of A equals to n means that the order of A is equal to n. So for instance, if you have that the order of an element is 3 with this notation, what that means is that A cubed is the identity of the group, A squared is not the identity, and A is not the identity. So this is the smallest, the number 3 is the smallest exponent for which that power of A gives you the identity. So that's kind of like a review of what an order of an element in a group is. Now, you will also need to review the division algorithm. So to do that, I'm not going to do this in this lecture. So please go and watch the video that I'm going to post a link here. So go and click on that video if you don't remember very well what the division algorithm says. So please do that if you don't remember it. Now, the third thing and the last thing we need to review for this is the well-ordering principle. That's because we're also going to use it in one of our proofs. So I'm going to do the same thing. So just go ahead and click on a link that I'm going to put somewhere here on the screen. Click on that link and watch the video to see what the well-ordered principle means, or what tells us about natural numbers. All right. So first thing I'm going to do is I'm going to prove a lemma. So that means it's a result that is going to be used in a theorem later. And the lemma says this. So let G star be a group. So that means G is the set, and star here is going to be the binary operation. And let's say we have an element A in G. So the lemma, what it says is the following. So if that element in G has infinite order, so that means no power, no integer power or natural power of A gives you the identity, and A to the n is the identity for n bigger than or equal to 0. The only way that could happen is if n is equal to 0. So assuming if A to the n is the identity, you get that n is equal to 0 provided that the element has infinite order. Now this might seem like it's easy thing to have and maybe trivial, but still requires a proof. And we're gonna use here one of the things that we reviewed earlier. So the way we're gonna prove this result is by the lemma is by contradiction. So by contradiction basically says we're gonna assume the negation of the conclusion. So we're gonna assume that n is not equal to 0, and we're also gonna assume that a has infinite order and the nth power of a gives me the identity. So that's what we're gonna assume here. So we assume that n is not equal to 0, the a has infinite order, and that a to the n is the identity. With these three things, we're gonna try to arrive to a contradiction. That's what the proof by contradiction is. So let's see how we do that proof by contradiction. So I'm gonna take a set here, and the idea for the proof by contradiction is we're gonna actually prove that a will have actually finite order. So that will be the idea. And the well-ordering principle is gonna play a big role here in this proof. So for the proof, we're gonna consider this set, the set A of all the elements, the natural numbers, for which the n power of a is the identity. But if you want to describe it in words, are all natural exponents m, for which a to the m is the identity. So this is, remember, this is the set builder notation for a. We're gonna apply the well-ordering principle to this to show that a will have finite order. So that's basically the idea. And that's what I say here. So we want to show that a has a minimum by using the well-ordering principle. So that's the plan. The plan is to use the well-ordering principle for this set A that is here. Now, if you already watched the video of the well-ordering principle, to use the well-ordering principle, we need to check two things. The first thing we need to check is that the set A is a subset of the natural numbers. That's the first thing. And the second thing you need to check is that the set A is non-empty. Both things are important to check. If you don't know why, go back and watch the video on the well-ordering principle. Now, let's talk about the A here. Now, A is clear. Why is that clear? Why is A included in the natural numbers? Well, if you look at the definition of what A is defined as the m's in the natural numbers so that they have this property. So A is made out of elements from n. So that means A is included in it. So I'm not going to say much about that because it's basically just from the definition. Just look at the definition of A. If something is in A, then in particular has to be in n. So that will prove that A is included in n. Now, let's check the second part. The second part will be to check that A is not empty. So we can also see that this statement is true because what do we know? We are assuming by contradiction that A to the n is the identity by number 3. And n is a natural number. So that means that n belongs to the set A because in A contains all the natural numbers which the power of A gives me the identity, and that's exactly what we have here. So n is in A, so A is not empty. Now, because A is a subset of natural numbers, is not empty, by the well-ordering principle, A has a minimum. So this set that is here has a minimum element, so it has a minimum natural number for which the power is the identity. So that's what it says right here. Now let's call that a naught. A naught will be the minimum of that set. So what does that mean? So that means that n0 will be a natural number, and A to the n0 is the identity of the group, and n0 is the smallest with these properties. Because that's what we're applying the well-ordering principle. We are finding the smallest element of A. An element of A is a natural number for which the power of A is the identity and is the smallest with that property. That means then that n0 is the order of A because the order of A is the smallest exponent, natural exponent for which A is the identity. So that means that n0 is the order of A, and this is of course a contradiction because we were assuming that A has infinite order, so that would prove the lemma. So let me scroll up here to check out the lemma one more time. And so if we have an element of infinite order and a power of that element gives me the identity for that exponent bigger than or equal to 0, so that exponent is has to be 0. All right, so we just proved that lemma. So let's continue with the next result, which is basically just now the criterion to check when an I power of A and a J power of A are the same. So this is the main goal of the lecture. All right. So let's look at what the statement of the theorem is. So in this case, what we have is, let's say we have a group G comma star. So G is the set and star is the binary operation, and we have an element of G. Now, if the element A has infinite order, in that case, and A to the I is the same as A to the J, then the exponents are the same. But that's only under the assumption that A has infinite order. Now, if A has finite order, the story is a little bit different. So if A has finite order, let's say order n, with this notation, remember that this notation means that the order of A is n, and we have that A to the I is the same as A to the J, then in that case, I and J are not necessarily the same, but in this case, it means that n divides the difference of I and J. So n divides I minus J. So when A to the I is equal to A to the J, what is the relation between I and J? It depends on whether A has infinite order or whether A has finite order. So the exponents could be the same, or the difference of the exponents must be divisible by n, which is the order of A. Okay, so let's do the proof. So this proof is actually two parts. So we have to prove two statements, the statement number 1, statement number 2. So let's go to statement number 1. So to prove a statement number 1, we have to assume that A has infinite order and that A to the I is the same as A to the J. I'm gonna call this here, I'm gonna call number 1. So we're gonna look at two cases. This is the number 1. So we're assuming that A has infinite order, and assuming that this is true, we will actually prove that I is equal to J only under the assumption that A has infinite order. So we're gonna consider two cases. The first case will be what happens if I is bigger than or equal to J, and the second case is when I is less than or equal to J. Now, case number 1 is this one, when I is bigger than or equal to J. So in that case, we're gonna use the binary operation star. We're gonna start on both sides of this number 1, and this number 1 right here, by A to the minus J. Okay, and we can do that because we have a well-defined binary operation. So if we have that A to the I is equal to A to the J, I can start on both sides by A to the minus J, which is what we have right here. Now, if we use the properties of exponent in groups, we can say this A to the I star A to the J is A to the I minus J, and that's a property that is valid in groups for exponents. Now recall, we talked about this in class, not all properties of exponents are true in groups. And on this right hand side, if you apply the same property, you just add the exponents, you get 0. And by definition, A to the 0 is just the identity. So what we can conclude from all of this is that A to the I minus J is the identity, and I minus J is bigger than or equal to 0. Why? Because we are under the assumption that I is bigger than or equal to J. If you recall the lemma we proved is that when we have an element of infinite order, which is the case here, A has infinite order, and a natural power of that is the identity, which is the case, I minus J is bigger than or equal to 0, and both of them are integers. So we have an integer that is bigger than or equal to 0. So it's a natural or 0. By the lemma, the only way that that's possible is if that exponent is itself 0. So I minus j has to be 0, or is the same as saying that I is equal to j. So we prove that I is equal to j under the assumption that A has infinite order. Now that's only for the case number 1, when I is bigger than or equal to j. Now what happens in the other case? When I is less than or equal to j, you can imagine that the proof is going to be similar. So if I is less than or equal to j, what you're going to do in that case is, I'm going to write it down here, you're going to start on both sides, by I a to the minus I. And the proof is pretty much the same as the proof we did for the case number 1. So I'm not going to do it again. Just start on both sides by this element and follow the same steps we follow here with almost exactly the same argument. So I'm going to say that number 1 is already proved. So in either case, we have the I is equal to j. So this proves now part 1, which means that the exponents are equal, provided that the element A has infinite order. So for the second part, let's look at that one. So we assume that the order of A is n for some natural number n, and we also assume that A to the I is equal to A to the j. Now in this case, the exponents might not necessarily be equal, so we have to prove that n divides the difference of these exponents. So I'm gonna call all of this number 2. So we're gonna start almost the same way we did with the first part, which is we're gonna start on both sides of this equation here by A to the minus j. Following the same algebra we did before. So if you take this and you start on both sides by A to the minus j, following this same algebra that is here, we're going to conclude that A to the I minus j is equal to the identity. This algebra here does not depend on whether A has finite or infinite order. So it's the same for both cases. So in that case, we can also conclude that A to the I minus j is the identity, and I'm going to call this one number 3. Alright, so in this case, this is the case where we're going to apply the division algorithm. So we're going to apply the division algorithm where I minus j is the dividend and n is the divisor. So basically what we are doing here is take I minus j and divide it by n. So if you do that, then you're going to have a quotient and a remainder. And that's what it says here. So then there are unique integers, q, that's the quotient, r, the remainder, such that when you take I minus j and divide it by n, so I minus j is q times n, that's the quotient, times the divisor, plus the remainder. And remember, that is an important part of the division algorithm too, which is that the remainder must be bigger than or equal to 0 and less than n. So I'm going to call this one number 4 and this one number 5. Now, the goal of this part is to prove that n divides I minus j. That will be proven as if we can show that r is equal to 0. So that will be the goal for the rest of this proof, to check that r is equal to 0. Okay, so that's what we're going to do. Now, I'm going to take this number 4 here, that I minus j is this expression here, and I'm going to plug that into this expression here, number 3. So I'm going to replace I minus j here in this expression, I minus j, I'm going to replace it with q times n plus r. So if I replace that in here, that's going to give me the following thing. That's going to give me that a to the q times n plus r, which is I minus j, is equal to the identity, because that's coming from number 3. Remember, this is the expression number 3 when I replace I minus j by q times n plus r. So we're gonna do a little bit of group algebra, if you want to call it that way here. Now this expression that here I can express it as a to the q times n star a to the r. That's because that's properties of exponents, laws of exponents for groups. We can actually simplify a little bit more and write down this a to the q to the n is exactly the same as a to the n to the q. This we can do it because that is also true for groups. So those are properties of exponents that are also true for groups. So we just put it here. But there's one thing we can use here. Because a has order n, a to the n, this one, is the identity. So I can replace a to the n by the identity. So that will give me a e to the q star a to the r is the identity. And just I say it right there here. The reason is because a to the n is the identity since the order of a is n. So that means I have e to the q. But e is the identity. The identity of a group to any exponent, integer exponent, is the identity again. So that gives me the identity. Star a to the r is still the identity because on this side, I'm always going to have the identity. The identity star any element of the group is the identity. So that means I can simplify all of this into a to the r. So I have the a to the r is the identity. I'm going to call that number 6. Now, if you go back and look at what 5 said, 5 said that this exponent here, remove as the remainder of the division. The remainder of that division is bigger than or equal to 0 and less than n. Now, since n is the order of a, because we are assuming that a has order n, n is the smallest natural number for which a to the n is the identity. That is the definition of the order of a. But from number 6, I have something that is less than n that also gives me the identity. That means that this r cannot be positive, because if it is positive, then this r will be the order, which contradicts the fact that n is the order of a. So from 5 and 6 here, then we'll have to have that r is 0. So let me say that argument again, because n is the smallest exponent for which a is the identity. R cannot be strictly bigger than 0. Otherwise, r will be the order. But we are saying that n is the order. Nothing can be less than the order if the exponent gives me the identity. So the only way that r can be here is 0. So if r is 0, if you replace this into the division algorithm that we had in 4, remember that I minus j was equal to q times n plus r, but we already proved that r is equal to 0. So what that means is that I minus j is equal to q times n, and this expression here means that n divides I minus j. Why? Because this is an integer, q. So this shows that n divides I minus j, and that will be the end of the proof. So that proves the goal we wanted to have for this lecture. Now I'm gonna scroll all the way up to the theorem again and emphasize what the theorem says. So the theorem is telling you when a to the I is equal to a to the j. When that happens, will that happen when I is equal to j all the time? Well, yes, if a has infinite order, but if a has finite order, a to the I is equal to a to the j, and I and j are not necessarily the same number. The only thing that they have to have is that n divides I minus j. So this will give you a criterion to check when two of these expressions are equal, depending on the exponent of what they have. So that's all I have to say for this lecture. Take care. Good luck.